If f is a kth degree polynomial, then it has at most k distinct roots, which might be real or complex. But what if we're working mod n? We've seen that this is not true in general. For example, 4x congruent to 8 mod 12 is a first degree equation, but it has 4 distinct solutions. So might kth degree polynomials have more than k distinct solutions? So let's start by considering primes. The fundamental theorem of algebra is related to a fundamental property of the real numbers. If a and b are real numbers and their product is 0, then either a is 0 or b is 0. Because of this, we know that if we can find a root x equal to a of a polynomial, then we know that x minus a is a factor where the other factor is a polynomial of lower degree. But is this always true mod n? For example, if possible, let's try to find two numbers whose product is 0 mod 11, but neither one is 0. So remember, we can assume anything we want as long as it's explicit. So suppose the product is 0, then I know that the product is some multiple of p. So p, because it's a prime number, has to either divide a or b. But if p divides a, then a is congruent to 0. And if p divides b, then b is congruent to 0. And so this actually proves the zero product property mod p. If p is prime and the product is 0, then one of the factors must be 0. Now, if we're not dealing with primes, this doesn't always hold true. So we might try to find a product of two numbers that's congruent to 0 mod 12 where neither one is 0. So as before, if the product is 0, then the product is a multiple of 12. But this can happen for any pair where the product is a multiple of 12. For example, 3 times 4 is 12, that's congruent to 0. 2 times 6 is congruent to 0. 4 times 6 is congruent to 0. 4 times 9 is congruent to 0. So we see this nice zero product property of the real numbers doesn't hold for non-prime moduli. And we have a term for this. If the product is 0 but neither factor is 0, we say that the two factors are 0 divisors. A rather unfortunate and misleading term, but that's the term that we use. The fact that the zero product property does not hold for non-prime moduli suggests that the fundamental theorem of algebra might also fail. For example, let's consider x squared congruent to 1 mod 8. We could always use trial and error, and by trial and error we find solutions. So here we have a degree 2 polynomial with 4 roots. Now, again, it's easiest to begin with prime, so suppose our modulus is prime. Then, in that case, all congruences of degree 1 have at most one distinct solution. So the fundamental theorem of algebra is true for first-degree polynomials, which is the base case for an induction proof. Now, suppose the fundamental theorem of algebra is true for all polynomials of degree n equal to k or less. Let f of x be a polynomial of degree k plus 1. So remember, we can assume anything we want as long as it's explicit. And let x equals a be a root. So if x equals a is a root, then f of x is going to be x minus a times something, which is a polynomial of degree n equals k. Now, suppose x equals b is another root of f of x where a is not congruent to b mod p. Since f of b is going to be b minus a times g of b, and that's going to be 0, but because a and b are distinct, the difference isn't 0, then the only way for this to happen is g of b has to be 0. Which means all remaining roots of f must be roots of a polynomial of degree k, so there are at most k more distinct roots. Consequently, f itself has at most k plus 1 distinct roots. And this proves something that's called Lagrange's theorem, another unfortunate name because Lagrange had many theorems, but a polynomial of degree n has at most n distinct roots mod p when p is prime. Now, a useful thing to do in number theory is to look for the breakdown. Look where the proof breaks down. So while our theorem was proven if our modulus was prime, it wasn't entirely clear where it was used. And in fact, we used it where we showed f of b is a product, and since b minus a is not congruent to 0, then g of b is the one that has to be 0. However, this statement would fail if there were 0 divisors. So again, going back to x squared congruent to 1 mod 8, we can see that x equals 1 is one solution, and we have a factorization. If our modulus was a prime p, the only other solution would come from x plus 1 congruent to 0 mod p. But since our modulus here is composite, another solution could be found if the product of x minus 1 and x plus 1 was a multiple of 8. For example, if x equals 3, we'd get, and that would give us another solution.